So we saw previously that the function of meiosis cell division is to produce daughter cells, to produce gametes that have the haploid number of chromosomes, and they also show genetic variation. That's due to two main processes that are taking place in meiosis cell division. There's crossing over that starts and begins in prophase 1, and then we have independent segregation of bivalence that occurs in metaphase 1. And we looked at the fact in that independent segregation detail that this leads to different possible combinations of chromosomes, of maternal and paternal chromosomes within the daughter cells and the gametes being produced. What we have to be able to do is carry out a mathematical calculation that actually allows us to look at the different possible of combinations of chromosomes due to independent segregation by itself in the daughter cells and in the gametes. So it's a very simple formula. It is just 2 to the power of n. So we need to remember that that little formula will give us the different possible combinations of chromosomes in gametes that's being produced. N, nice and straightforward. N just represents the number of different homologous chromosomes, just as we've used that before. So let's work through it and do an example. So if we said that n is 1, what that's actually saying is that within an organism there's just one homologous pair of chromosomes. So I'm going to use two different colours just to represent maternal and paternal chromosomes. So this organism has got a diploid number of 2. They've got one homologous pair of chromosomes. Now we know that when meiosis cell division takes place, the daughter cells, the gametes that are formed, must A, have the haploid number of chromosomes. So we know that if diploid is 2, they can only have one per daughter cell. And the second rule is that you must have one chromosome from each homologous pair present. So this is quite straightforward. Where you've got n is 1, so 2 to the power of 1 is 2. And this is fairly simplistic. The only possible combination, therefore, that you can have is like so. So you've got one chromosome from each homologous pair, and the daughter cells, the gametes, are haploid. So that's a fairly straightforward one. If we were to look at another example, and so now n is going to be 2, i.e. we've got 2 different homologous pairs of chromosomes. So once again, let's just draw those in. So n is 2, we've got 2 different homologous pairs of chromosomes, we've got diploid number of 4. So again, we know that meiosis is going to produce daughter cells with haploid number of chromosomes, so it can only be 2 chromosomes per daughter cell. And we also know that you have to have one of each homologous pair present. So if we run through the the math side first. So we've got 2 to the power n, so n is 2, so 2 to the power 2 is 4. And we've actually used this example in a previous session. So we know we have to have 2 and one of each homologous pair present. So we could have that. We could have that combination. We could have that combination. And finally we could have that combination. So we have got 4 different possible combinations of chromosomes in the gametes, or in the gametes rather. Let's just go slightly higher again, and let's say that in this case n is 4. So we'd have 4 different homologous pairs of chromosomes. We'd have a diploid number of 8. I'm not going to draw all of those out because that will take ages. But let's just stick it through the formula. So we're using 2 to the power n, and therefore we're going to have 2 to the power of 4. So 2 multiplied by itself, 4 times 2 times 2 times 2 times 2, would mean you get 16 different possible combinations of chromosomes in those in the gametes being produced. And this then allows us to look at those different possible chromosome combinations. Again, I'll say it again, this is based purely upon independent segregation, and it's not including the effects of crossing over. The final thing that you might be asked to do is just to appreciate that when offspring are produced via sexual reproduction, fertilization is completely random, and therefore this and because you're taking 2 different gametes from 2 different parents with different possible combinations, this magnifies and increases the genetic variation in the offspring themselves. So in which case, again, we need to be able to use another formula, and this formula is 2 to the power n in brackets and then squared. And so what this formula represents is the different possible combinations of chromosomes in offspring being produced. So let's use the example that we looked at before of where the number of different homologous pairs of chromosomes was 4 in this particular species. So if we have a sperm, so male gamete, it's got 16 different possible combinations of chromosomes. Let's have an ova, not drawn to scale, from a different parent of the same species. So there's still 16 possible combinations of chromosomes based purely on independent segregation, and therefore when fertilization takes place and we have the zygote, the single-celled organism produced, offspring produced at the end of this, there are 16 multiplied by 16 possible combinations of chromosomes, and therefore in the zygote, in the offspring, there are 256 possible combinations of chromosomes that could be achieved. And if we just run that through the formula, so we've got 2, n is 4, and then you're squaring it, so 2 to the power 4 is 16, and then you're squaring it, equals 256.